All right, the goal of this video is to talk about how these number puzzles, where we have 2 times 3, the factors 2 and 3, resulting in a product of 6, and the terms 2 and 3 resulting in a sum of 5, this puzzle, is related to the quadratic representation tool here, and how that looks with algebra tiles and physical representations, and also to point out some pitfalls that occur from this model and how to address those. So first of all, just so that we really understand what's going on, I want to take 2 of something. I want to take 3 of something, so my 2 and my 3, and they add up nicely to 5. So we have our sum of 5. Now here's the thing, these things also have a product, and when we talk about a product, a useful way to model a product is as a 2-dimensional rectangle. So we have our 2 and 3, which have a product of 6. So it's kind of represented by the area in here. That's 6 right there. And it's useful to look at this model and recognize that that 2 is grouped together, and that 3 is grouped together. And the result of the product of those 2 groups results in this product 6. And likewise for this one that we want to look at, it also works the same way with this sort of model, but there's a few caveats. So let's look at it. First of all, we're saying that if we have a 4x and an x, the sum has to be 5x. So let's model that sum first. And let's keep them grouped, just like we did before. And again, when we're looking at algebra tiles, we don't know how tall an x is. So if we're going to put x's in different axes, they need to be on the diagonal because we don't know how long they are. They're x long. We could lower or change the size or something to represent that. Anyway, this right here implies a certain grouping and factoring like this. And voila, without doing a whole lot of math, we have just determined that if my factors are 4x and x, I get this 4x squared as a product and 5x as the sum. Where the heck is the 4x squared in this model? Well, I'll show you. It's not obvious unless you consider the cross products. So just let's go back to number land for a second. If we were to make area model out of numbers that has 4 cells like this. Let's say we're multiplying 12 and 15 like this. We can take our partial products here and add them up to get our actual product. And an interesting thing happens with those partial products. This cross product, 100 times 10, has to be equal to this cross product, 50 times 20. This is always true. It's really useful in vector math or in some linear algebra. And I don't know if it's anything other than the cross product rule, but this is a cool fact. And it stays true in quadratic land. So if we make our, what is this thing? This is 1x squared, there's 5x's, and there's 4 numbers here. We know that the cross products have to be equal. So setting this up in the same way as our model up top, this would have to be 4 right here, and this would have to be 1. There we go. So we get 4 x's right here, sorry, and then 4, and then 1x and an x squared. It matches our model. The cross products have to be equal. So that 4 times x squared has to equal 4x times x. And this is the trick. This is what we're doing in order to leverage this fact. This 4x times x, look at that. Those are the 2 terms that we've split up to group, and they have to be equal to the cross product, which happens to be 4x squared. And the cross product in this case is always a times c. If we're looking at a quadratic in standard form, it's specifically the first term times c. So ax squared times c is going to be that cross product. And we can leverage this fact in order to factor. That's what we're really doing here, is we're leveraging the cross product. There's a problem with this, though. If you're modeling this, there's actually another way to model this that is not the same quadratic. And that's where this gets a little tricky and a little sticky. just to give you an idea of going through the process, if I started with 4x and x, what if I chose to group them in this orientation instead? They're still grouped, but they're just in a different orientation. And now I have a completely different setup here. This now is 4x squared plus 5x plus 1, and we still get the same result up here. We still have our 5x, and we still have our 4x squared, and it's actually modeled with the tiles here. And a lot of students, if you give them these kinds of problems where they're missing maybe the sides, might try to set it up like this, or they could set it up like this. And based on this model right here, both of those are valid. This is x plus 1, just so that we're really clear, and 4x plus 1. And both of these result from this kind of model. And I did a little bit of a dive to try and figure out why this was the case. And it turns out that there's just multiple ways to solve a lot of these problems. And it's rooted in the relationship between the roots and the coefficients as described by Vieta's formulas. There's a thing that actually talks about this. And if you want to dig into why that happened, you can go look up Vieta's formulas and what they imply in terms of quadratics. The long and short for a teacher is, if you're going to give a puzzle like this, you know that there are, well, at least if you're only giving 2 of the possible parts, there's going to be ambiguous ways to represent this when you start this way. No matter what, if you're using algebra tiles or not, there are ambiguous ways to represent this, which means that this is an interesting way to try to factor, and it's a very useful tool when we already know the quadratic. But giving this as a puzzle related to the previous number puzzles that we already looked at, so these guys right here, these number puzzles, I don't know that that is probably the best use of time unless you're doing it as an exploration and you understand that things can get ambiguous and tricky because a doesn't have to be equal to 1 in a quadratic.